just consider the generalized Riccati equation like this. I don't think there is any published work on this kind of equation, or there is anything useful in solving this equation. But the theoretical use of program 10, we can easily solve this kind of problem. And to solve this problem is first to enter the four matrices and then define the anonymous function to describe the original equation, and then use random points and search points to solve it. And still we have to use the new, in the old version I only found 3 solutions and all satisfied. However, with the new versions, I run the program for 2 hours and found 16 solutions. Maybe you can try in your assignment how many more can you find. So I think you may understand this kind of loop program. First, to assign the original equation like this, and assign the solution matrix X as an empty matrix. Then I run the loop.
What is that plus?
Sorry? This one?
That's a plus in the normal in the function.
That's a matrix. These are all matrices.
What is the function?
You have to define it first before running this. It just explain it, right? I'm not going to run it. You have to define A and B, A, B, C, D matrices first, and then define this function. And then we set a record to all the equation solutions to act as entity ones. And then I can select a random number times 10,000 of a large one. If the random number is small, then it also tends to be a small one, so that's no problem. We can set a large initial search point, and then we can solve the equation. And if the solution of 10 is a solution to the equation, we have to see whether this solution is already exists in the X matrix. If it is exists, we do not have to record that one. I can just discard it. And we can use this one. If it is not the solution, then we can extract the matrix equation into a row vector. For this case, we have 9 elements to store in a row vector, and we can append this vector to the matrix. So in this case, we may find more solutions. To run this program, I found 16 solutions. Maybe if you run similar thing like this, you can find more solutions. I'm not quite sure how many solutions are there. And this part of the code I have appended in, I have given this kind of code in the assignment list, assignment 4. I listed the program itself. I can take a simple try of this. First, we have to specify the 4 matrices. And then I can run this code. Let's start it here. To see that size X, we have the matrix X as 3 rows, which means that we have 7 rows, we have 7 equations, and we have 7 solutions already obtained. And And if you run the program for longer time, maybe you can find more solutions to it. So in this way, you may list as more solutions as possible, but it is not guaranteed to list all the solutions. So this is a part of the assignment. Maybe if you run the program, you can find more solutions to the original equations. So now let's consider optimization problems. And in optimization problems, I'm going to present the topic in unconstrained optimization problems, constraint problems, and integer programming problems. Later on, I will demonstrate on dynamic programming problems. So now let's consider unconstrained optimization problems. The mathematical form for unconstrained optimization problem is something like this. And I do not want you to know too much about it. And just to know what is the physical meaning of this one, that's enough. If you are interested, you should read more papers or books on it. But to use it, what you need to know is just know what it means. That's enough. Physically, that means for vector x, where x can select any number, so we call it unconstrained. We do not have any constraint on the selection of x. The physical meaning of this is we want to find the value of x which minimize the function f of x, where f is a scalar function and this is called an objective function. So the standard minimization problem is to find the x which minimize this objective function, and x can be selected as any number, so we call it unconstrained optimization problems. Here x is a vector containing n numbers and f is a scalar. If f is not a scalar, we call it a multi-objective optimization. We shall not discuss it here. And x here also named as decision variables or optim variables. So this is the standard form of the optimization problems. It seems that there are limitations in the notation because we are only interested in finding the minimum number of function. What if we want to find the maximum number of x? It is also a topic of optimization problems. For maximization problems, what we need to do is to multiply the objective function by -1. Then it is mapped into a minimization problem. So, okay, no problem. So if I want to find the maximum number of f function, it can be converted minus fx. It's a minimum. So later we will only talk about minimization problems, and in fact it includes the maximization problems as well. So from now on we shall only consider minimization problems. So let's solve the problem